The last lecture we have to study the what is the sequence and what is the convergence of the sequence, and we take what is the comparison test 1, and by using comparison test 1 we solve some examples. Okay, so now limit form of a comparison test. Okay, test 1. Okay, limit form of comparison test. So what is the limit form of comparison test? So what is the theorem here? We shall prove the theorem also here. So let if summation un and summation vn are two positive term series, are two positive term series, such that what is the limit form of the comparison test? So that is the limit of un upon vn, as n tends to infinity is some finite number L, where L is a non-zero and finite, where L is a non-zero and finite, then the two series behave alike. Two series are behave alike. So what is the behave alike? So see here, so summation un and summation vn be the two positive term series, each terms in that series are positives, such that a limit of un upon vn. So these are the n terms. So limit of un upon vn is some non-zero and finite number L, then the two series behave alike. So what is it means? What is mean by behave alike? If this series is convergent, if un is convergent, then vn is also divergent. If vn is divergent, then summation un is also divergent. So it is called behave alike. So what is the proof of that theorem here? Proof. Okay. So since summation un and vn be two series of positive terms here, so here we have some finite number L greater than 0 L, so implies that L minus epsilon also greater than 0. However, epsilon is very small, for epsilon positive, very small. So if L is greater than 0, then certainly L minus epsilon also greater than 0 here. Okay. Now, so we take, so that is given here. Then prove that behave alike. So now limit of un upon vn as n tends to infinity, so that is L is given here. Okay. So what is the definition of limit of the series? Epsilon definition. So that is we studied this in a sequence. So therefore there exists a positive number m, such that, so by definition of a limit in a sequence, so that is un minus vn divided by minus L is less than epsilon whenever for all n greater than equal to m here. Okay. So what is the definition of a limit of this? So this implies that, so this is very simple one, so that is we discuss many times. So what is this? This is less than un divided by vn is less than L plus epsilon for all n greater than equal to m. So this implies that this, okay, so we discuss in many theorems. So how this can write in this form? So this is very easy. We have not repeated here again. Okay. So what happens? So this is L minus epsilon multiplying throughout by Vn less than Un less than L plus epsilon into Vn for all n greater than m. N greater than m. So this is, we say this is equation number 1 here. So for all greater than m also here. Okay. So from 1. So from 1. Okay. So what happened here? If Vn, so we take this part. If Vn is a convergent, if the series Vn is a convergent, then we say that, then if this series, so Vn is convergent, then by using this inequality here, so Vn is series, Vn is convergent, then automatically, so then the series Un is also convergent. Okay, no doubt, clearly. So from this part of this this inequality, so if so what happened here? So if Un is greater than equal to, so this is taking this part, L minus epsilon Vn, then what happened if summation Vn, so this is series, is divergent, then we say that by using this, if Vn is divergent, then the series Un is divergent, is also divergent here. Okay, this is very simple. So if one is convergent, then other also convergent series. If one divergent, then other also divergent series. Then hence the two series summation Un and summation Vn behave alike. Means one convergent, then other also convergent. If one divergent, then other also divergent. Hence the comparison test 2, and this is the proof of the test 2 here. So we take example, very simple examples. We solve that example by using comparison test. So sorry, limit form of, no, comparison test 2. So this is limit form of comparison test. By using that test, we solve some examples. So take example, very simple example. Test the convergence of the series. The series is given, very simple series, summation 1 upon square root of n plus 2 plus root n. So solution. Here Un is the nth term of that series is what? So that is root n plus 2 plus root n. Okay. So we take, what is Vn? So this is our choice. We take, what is Vn? Vn is 1 upon root n. So we take here this. Okay. So Un is this and Vn is this. So therefore, what is the limit? So we check the limit, is it finite or not? So limit of, what is Un upon Vn? So this is limit as n tends to infinity. What is un? Un is what? So this is root n plus 2 plus root n divided by this Vn 1 upon root n. So this can be written as limit as n tends to infinity. Okay, so this is a root n upon root n plus 2 plus root n. Okay, so dividing this to numerator and denominator by 1 upon root 2 divided by 1 upon 1 upon root n, and this is also divided by root of n, 1 upon root of n. Okay, so limit as n tends to infinity. So what happened? Dividing this by root n, so this is 1. So dividing this by root n, so this is n get cancelled, 1 plus 2 upon n. Dividing this by root n, so this is plus 1. So what is the limit of this? So the limit of this is put n as n tends to infinity, so this is tends to 0, so that is 1 root 1 plus 0, 1 plus 0 plus 1. So this is 1/2, and this is a not equal to 0. This is a not equal to 0. L is non-zero. Okay, and finite. Therefore, we get this here L in this form here. Okay. Then by comparison test. So limit form of comparison test, un and vn series to behave alike. Okay, behave alike. So we test here, is it convergent or divergent? We don't know. So what is vn here? Here vn, but what is vn? Vn is 1 upon root n. So this is what? 1 upon n raised to half. And this is p series here, n raised to p. But p is equal to what here? So this is a p series, but p is equal to half. And this is less than 1. And in p series, if p is less than 1, then the series is divergent series. Therefore, the series Vn, which series Vn, so this is summation 1 upon root n, is divergent. Then by comparison test, limit form of comparison test, if this series is divergent, then this series also divergent, because the two series are base alike. Therefore, the given series is a divergent. Very simple example. Divergent, okay? So we take another example. So take example. So very simple example. So test the convergence of the series summation sine 1 upon n. Okay, this is the series here. Okay, summation 1 upon n. So test this convergence of that series here. Okay, we solve similarly. Okay, very simple. So what is un? Un is what? Sine. So this is a sine. N, the term of that series. See, that is sine 1 upon n. So okay, sine 1 upon n. So we choose Vn is 1 upon n. We choose Vn is 1 upon n. So limit of un upon Vn. Limit of un upon Vn as n tends to infinity is equal to limit as n tends to infinity. What is the un? Sine 1 upon n divided by 1 upon n. Okay. Put 1 upon n is equal to x, something x, 1 upon n. So as 1 upon n. As n tends to infinity, as n tends to infinity, x tends to 0. X tends to 0. Therefore, this limit becomes a, so limit as n tends to infinity, un upon vn is equal to limit as n tends to infinity. So put it 1 upon n is equal to x. No, x tends to infinity here. Just x tends to infinity. X tends to 0. X tends to 0. Just put it 1 upon n is equal to x, as n tends to infinity, x tends to 0. So this limit become here. So put 1 upon n is equal to x. So sine x divided by x, and this is standard limit. So this is 1 here, and this is not equal to 0. So L is 1. So L is non-zero and finite. By comparison test, both series summation un and summation vn behave alike means to in sense of comparison, in sense of convergence and divergence, the both series are same here, so that is behave alike. Okay, but what happened here? So what is vn here? So vn is 1 upon n. 1 upon n. So that is 1 upon n. So 1 upon n. So this is also p series. So this is p series here. P series. 1 upon in the form p series. P series. But what is p? P is 1. P is 1. P is 1. P is 1. But in P series, so what is a P series? So this is a P series here. P series. And if P is equal to 1, then the series is divergent series. So we already studied P series and what is the convergence and divergence of that series. So if P is 1, then the series is divergent series. So what happened? So P is equal to 1. Therefore, the series is divergent. Which series? 1 upon n. So this series is a divergent series. The series is divergent series. And both by theorem, both behave alike by using this limit. Both series are behave alike. And if the series summation 1 upon n is divergent, therefore the given series, this series is also divergent. So this is very simple example here. Okay, so we take more example of this type. So that is a limit form of comparison test by using that test here. So take another example, very simple example. Test the convergence of 1 upon 1 into 2 into 3 plus 3 upon 2 into 3 into 4 plus 5 upon 3 into 4 into 5 3 into 4 into 5 and so on here, plus and so on. Okay, so test the convergence of that series. So in this series, what is the nth term? So that is nth term is 2n plus 1 divided by n into n plus 1 plus n plus 2 here. Okay. Okay. So what happened here? So that is what happened. So this nth term of that series. So put a n is equal to something 1 here. So we get this. So that is 1 into 2 into 3. Sorry. 1 into 2 into 3. Put n is equal to 2. Then there is a 5, 2. I think something just n is equal to 1. So 1 upon n is equal to 0. So that is what happened here. So 1 into, no. So this is 3 upon 3 into 2 into 4. So then what happened? Put n is equal to 3, 3. Okay. So that is un is equal to this here. So choose. Let us choose another series. So that is Vn is equal to something 1 upon n square. 1 upon n square. Okay. So this is a given series and we take another series for the comparison. So and the nth term of that series Vn is equal to 1 upon n square. So therefore limit of un upon Vn as n tends to infinity is equal to limit as n tends to infinity. So what happened here? So that is un is what? 2n plus 1 divided by n into n plus 1, n plus 2. Okay, divided by, what is Vn? Vn is 1 upon n square. Okay, so therefore, so this can be written as, so that is, this can be written as limit as n tends to infinity, n square into 2n plus 1 divided by n into n plus 1 into n plus 2. So dividing by numerator and denominator by n cube, so that is multiply by 1 upon n cube to numerator 1 upon n cube. So dividing the numerator by n cube and also denominator by n cube, so we get here limit as n tends to infinity. Limit as n tends to infinity. So what happened here? So that is, so n square it cancel, remaining n, also divide this, so that is a 2 plus 1 upon n, okay, 2 divided by n cube, n cancel, so also n divided by n, so that is 1 plus 1 upon n, also divided by n, 1 plus 2 upon n, okay. So then what happened? So this is, so limit as n tends to infinity. So this limit is 1 plus, so n tends to infinity, 1 upon n tends to 0. So 1 plus 0. So this is 1 plus 0, 1 plus 0. Okay. So this is 1 here. Okay. So this is 1. Okay. No. This is 2 here. 2. So this is 2 and this is a not equal to 0. Okay, this is L, non-zero and finite, no doubt. Therefore, by comparison test, summation un and summation vn, those series behave alike, behave alike. But okay, but we take series Vn. Series Vn is what? Summation Vn. So that is summation 1 upon n square. And this is P series 1 upon n raised to P, where P is equal to 2. P is equal to 2. So this is greater than 1. And in a P series, if P greater than 1, then the series is a convergent series. Therefore, the series Vn summation 1 upon n square is a convergent series. Okay. Then by a comparison test, behave alike means if this is convergent, then the given series is also convergent. Therefore, the given series is convergent. Hence the example. Okay. So these are the very simple examples solving here by using limit form of comparison test. So very simple example. So now we discuss the comparison test 2. Comparison test 2. So what is the comparison test 2? And taking example on comparison test 1. So already we have taken in the last lecture what is the comparison test 1 and taking example. In this lecture we take limit form of comparison test, okay? And what is the next part? So that is the comparison test 2. Comparison test 2, okay. So what is the statement of the comparison test 2 here? So that is a theorem we say. So that is the theorem. If summation un and vn be two positive term series, we remember in a comparison test both series must be positive. So be two positive series, positive term series, and there exists a positive number and there exists a positive number m such that un upon un plus 1 is greater than equal to vn upon vn plus 1 for all n greater than m. Then what happened? Then if summation vn, if the series vn is convergent, then the series vn is also convergent. Notice b, if summation un is a divergent, then summation vn is also divergent. So what is the comparison test 2? If un, summation un and summation vn are two positive term series and there exists a positive number m such that if un upon un plus 1 greater than equal to vn upon vn plus 1 for all n greater than small m, and then if vn is convergent, then vn is convergent, then un is also convergent, and if un summation is divergent, then vn is a divergent. Okay, so this is the comparison test 2. So we shall take the example by using solving by using that test in the next lecture. So okay, thank you.